All right, so now we're on our last conic section, and obviously hyperbolas. So with hyperbolas, very similar definition, set of all points xy. Xy again meaning, of course, that it's on a plane, for which the absolute value of the difference means that we are subtracting, between the distances from two distinct points, so two distinct points are our foci, is constant. So because we have a difference instead of a sum, as you can see in our equations, we are going to be subtracting. Whoa, I definitely have an error here. Make that subtraction. I copy and paste. So we have a difference as you are subtracting in your two equations. Again, our center is HK. Ideally, if we can have our center be at the origin, we definitely want to do that. We have two situations. We have our transverse axis is horizontal and our transverse axis is vertical. Well, with a hyperbola, the first fraction tells us so much information. And it's obvious here, like this variable is x compared to if you have a vertical axis, it's y. And we have our vertices. A still represents the distance from your center to a vertex point. And so A is always in the first fraction, which is different than the ellipse. Ellipse, it can switch because we always, with ellipse when you're adding, addition is commutative, so we can switch it back and forth. It doesn't matter. Where here, that first fraction tells us so much information. So you really look at that first one. So if we look at a transverse axis, it's horizontal. I'm going to draw the center at the origin. So there's my center. If x comes first, I know that my parabola, the two branches of the parabola, are going to intersect the x-axis. I'll try to make them evenly spaced here. So because x is first, this is what it's going to look like. If we go over and if we have our transverse axis as vertical, if y is our first variable, well then our branches are going to intersect the y-axis. And try to make them evenly spaced if our center again is at the origin. So that's the difference between the two. A is still representative of our vertices. So if we go from our center to a vertex, just like the ellipse, is always on your conic section. So this is representative of A, and this would be a vertex point, and I'm labeling it with a V again. This obviously then is also a vertex point, and if we look at the other hyperbola, when we go up, this would be a vertex point. That distance again here is A, and then down here this would be a vertex point as well. To write in a couple things, and then we will go back to the graph. For a transverse axis, it's a line segment connecting the foci and vertices. So to write this in, line segment connecting foci and vertices. I'm running out of room. So transverse axis. Our vertices are where our transverse axis intersects the hyperbola. Maybe where the transverse axis intersects the hyperbola. Remember, vertices are always on your conic section, and that's true for our parabola. Our vertex point is that bottom or the minimum or the maximum is what it could be. It's true for the ellipse, and it's also true for our hyperbola. Vertices are always on the conic. And we don't have covertices. So in the equation we have this B, but that does not represent covertices for a hyperbola. We do have asymptotes, and asymptotes help us draw the branches accurately. Remember, we always approach an asymptote. My way of remembering things is that if I'm drawing, if I'm going to draw an asymptote, the equation of it is always going to be a line. Well, in order to get the slope of a line, we know that slope is rise over run. Well, you rise with your y's, y-axis always rise. You run with your x's. So for this first one, and your asymptote always goes through the center. And remember, the center doesn't have to be at the origin. If we have a word problem, we're always going to try to make it at the origin. That's definitely the easiest. But to graph accurate branches, because they can be really wide, they could also be really narrow, we always have to account for our asymptotes. So really, if we just say what the slope is and know that it has to go through the center, if you have to write the equation, it's very easy if your center is at the origin, because then we know our y-intercept is 0 and we just have to account for put the slope in. If your center is not at 0, then you can write the equation by taking your center, because that has to be a point on the asymptote, and also the slope. So we're just going to say what the slope is, and your slopes here are going to be opposites of each other. So in this situation, our slope is equal to, it's the positive and negative, because obviously this one is positive, where this one is negative, and I always think of it as rise over run. Well, rise with my y's, so that means it's b, divided by, I run with the x-axis, so I'm dividing by a. So it's a very easy thing to remember for slope if it's rise over run. Remember, that is just the slope. You have to continue and write the equation, but you can always find a point on your asymptote, because the center, it always has to go through the center. If you look over at a transverse axis is vertical, and we find our slope, again, of our asymptote, so if we draw them in, they'd look something like this. Our slope now is going to equal, it's positive or negative, and then keep the same idea in mind that it's rise over run. Well, you rise with your y's, so here's y, you rise, then it's a. So obviously take the square root of whatever that is, because your equation is a squared. And then you run with your x's, so rise over run, that would be a over b. And I don't really memorize anything with it, because I've dealt with slope for so long, I know how to deal with slope. Slope is rise over run. If you keep that in mind, it's a very easy thing. So asymptotes, you do have to write the equation, and so we're going to put in here that it is equation. 1 point always is at the center. So the center of the hyperbola is always on the asymptote, or asymptotes, you can make it plural. And then your slope obviously differs with if you have a transverse horizontal axis compared to a vertical axis. You can write them both in if you want to, that your slope is either plus or minus b divided by a, or slope will equal positive or negative a divided by b. So writing the equations isn't bad. You will have to graph those to make the branches accurate, like I had said. All right, so now we have our foci. Our foci are incredibly important. If we look back at our definition, is that we know that the absolute value of the difference between the distances from our two distinct points are our foci. So on our, if we're talking about the horizontal, my foci are going to be here and here. Again, they would be evenly spaced. With your foci, when you, for the definition, it would be here to, I'm going to my, to one of the branches, and then here. So if I take this distance and subtract this distance and take the absolute value, I'm going to get a number. Well, that number is constant, so if I pick a different point, so if I go from like here to here and subtract from there to there, I will get the exact same constant. So a similar idea to the ellipse. Ellipse, if you add them together, the two distances, you're going to get a constant. Well, with a hyperbola, it's a difference, and that's why in your equations you have to be subtracting. So to write down something about our foci, Our foci are two distinct points in which the branches of the hyperbola go around. So two distinct points in which the branches of the hyperbola go around. Lastly, besides the eccentricity here, but we do have an equation, because if you look at an equation to find your foci or to find A and B, just like you had with the ellipse, obviously if you have an equation, you don't know what your foci are. So in order to find it, let's make just a box here so that we remember it's a pretty big idea. In order to get to our foci, this time it's going to be a squared plus b squared, because we know we have to go farther out. So it's a squared plus b squared, and that will equal our c squared. C is just like it was with our ellipse. It's the distance from your center to your foci. So we could draw in on our graph, which is now getting very cluttered, that distance is c. So nothing changes. Obviously this is the Pythagorean identity, but it makes sense that you have to add, because here's a, if you have to get to your foci, you're going to have to add to it. It's farther away. So a squared plus b squared equals c squared, and you will end up using that equation a significant amount. And the last thing then is eccentricity. Our eccentricity, same equation that we had with our ellipse, it's c divided by a. In this situation, our c value is always greater than our a value. Therefore, eccentricity is always going to be greater than 1. If your eccentricity is very large, then your branches, just for a quick sketch, your branches are really wide. Try to make it look somewhat symmetric. If the eccentricity is small, then our branches are really, really tight. They're really narrow. And with word problems, I prefer, those aren't very symmetric, sorry. If using word problems, I prefer to have a horizontal transverse axis. It's totally up to you, but it's kind of a preference thing. I think we deal with those a little bit more often. And just keep in mind that that first fraction is so incredibly meaningful. It tells us, you know, how the branches are going to open, and it tells us also where our vertices are. So keep that in mind. We have a couple examples here. The first one is very similar to the others that we did with the ellipse and parabola. Find the center, our foci, and vertices of the hyperbola, and then sketch its graph using asymptotes as its aid. Looking at it, we know that we have a hyperbola right away. We have y squared and x squared. Well, because they're both squared, that rules out our parabola. We're subtracting, so it's kind of a hint as well. And just like we've done in the past, we want to group our variables. Therefore, I'm going to have my y squared, and I don't have anything that goes with the y, which is fine. And then I have to subtract, and here's where it gets a little bit interesting. If you are subtracting, and you have 9x squared here, but you group this thing with parentheses, if you want to put your 36x, if that's positive, this has to become a negative 36x. So be very conscious of that, because then we have minus a negative, which is what we wanted. It was positive to start. I am going to complete the square, this negative 72 again, I don't particularly want, so I'll put it out over onto the right side. My leading coefficient has to be 1 in order to complete the square, so if I factor out a 9, I have x squared minus 4x, leave my space, this is equal to 72. Half of 4 is 2, 2 squared is 4. And now we have to be very conscious as well. So this negative with hyperbolas tends to get us, because we have a negative 9 times a positive 4 if we distribute. So really on this side, I put in a negative 36. Well, if I just subtracted 36 from the left side, I have to also subtract 36 from the right side. So hyperbolas, you have to be very conscious that negative, that subtracting, makes it much harder. Therefore, we have y squared minus 9 times, it would be x, keep our subtraction, that becomes 2, that quantity is squared. 72 minus 36 gives us 36, and just like the ellipse, your equations have to equal 1. So divide both sides by 36, and my equation is y squared divided by 36 minus 9 divided by 36 is going to give me 1/4. And then we have the x minus 2, that quantity squared, equals 1. So the first thing to find is our center. Our center, make sure you look for your x's first. X is 2. Our y value, it would be 0. I know it says foci next. I'm going to jump to vertices. Vertices, remember, are always in that first fraction. This first fraction is incredibly important to us. So because your vertices are always, if you look back at the top of your page, it's always either y squared divided by a squared or x squared divided by a squared. That always represents the vertices. Therefore, my y's have to move by 6. So then I have 2. Well, they were at 0, so I can add and subtract 6 to get to my vertices. And then for our foci, again, foci and vertices always, whether you're dealing with an ellipse or a hyperbola, they're always on the same axis. So again, my y's are going to move, but in order to find our foci, we have to find our c value. Well, to do that, this is a squared, here is b squared, and our formula says to add them together. So if we have our a squared plus b squared equals c squared, a squared is 36 plus b squared is 4. That tells us that 40 is equal to c squared. If we take the square root of 40, we can break down and simplify, and it should be 4, I gotta think of what it should be. Two square root of 10? Why do I feel like that's not right? But I think it is. I'm leaving it like that. So it's 2. From 0, remember we always change from our center. It's plus or minus 2 square root 10. And if I've calculated this wrong, help me out. Or change it. Yeah, let me check real quick. I don't know why I wrote something else down on my paper, but I probably just screwed up that time. Well, it's larger than 6, so at least we know we're in the right idea. We're going to leave it like that. Now it also says to sketch, and I do want to sketch this one on a test or quiz. I would put a grid in here if I want you to sketch, so that you can put the graph the asymptotes properly. And if our center is at 2, 0, so here's our center, it's 2, 0. Remember, your asymptotes have to go through that. Well, the next thing is we have to figure out what is the slope. Your slope, remember, is always your rise over run. So I rise with my y's, so slope will be 6. I'm going to run with my x's, it's a square root of 2. Therefore, my slope is going to be positive or negative 3. And from here, I gotta put in some more marks here. And if you just have 2 of them, you can make a line with 2 points, so that's all you really need. So now I rise 3, run 1, and get my ruler out to connect them. May not be perfect, but it'll work. I also can rise 3 and go back 1. So now we have our asymptotes. They have to be accurately sketched. Our vertices are at 2, positive, and negative 6. So 1, 2, 3, 4, 5, 6. Oh, good, I squeezed that one in there. And then to -6. And we know that this is right, that it should be opening up and down, because y was our first variable. So then we can graph it. They have to get closer and closer to the asymptotes. And we have a general idea what it is. For your foci, if the 2 square root of 10 is 6 point something, so your foci would just be a little bit farther in there. And that's obviously just going to be an approximation, but it's good. We get the general idea where it is, and you should approximate it. Put it in there, make sure that you're approximating a decent amount. So we found our center, we found our foci, our vertices, and then we sketched our graph. So make sure that you sketch these things accurately again. All right, number 60. Now we want to write the equation of a hyperbola, and they give us a couple, they're actually 4 points. So they tell us our vertices and our foci. Some of you are much more talented and gifted than I am and can figure out how to do these things without sketching. I totally recommend sketching because I think it's really, really easy, and they are purely sketches. So if I have vertices at 2 plus and minus 3, so 2, positive 3, there's a vertex. 2, negative 3, there's a vertex. I know that my branches are going to open like this, up and down, which tells me that y squared is going to, or y squared is going to be the first fraction of my hyperbola. Our foci are at 2, 5, 2, -5. Great, we put them in. We know that our branches also always go around our hyperbola. The next thing to figure out is that we have to graph, or in our equation we have to have the center. Well, in this situation, center is very easy to find. It's 2, 0. So not too much different than the one that we just had, and that's okay. If we write our equation of our hyperbola, then we have to account for our center. Well, for your y, your center is just at 0, so that just stays y squared. It's divided by something. I'll fill that in a second. Minus x, our center is 2, so it's going to be x minus 2, that quantity squared. And I know that this has to equal 1. Don't forget to set it equal to 1. We're writing the equation, so you better have an equal sign in there. Now we know that in this first fraction, the distance from our center to our vertex is going to be that a that we need in the denominator. So center to vertex, okay, great, that's 3. 3 squared is 9. Therefore, I can write down, I know that a is 3. We also know that c, the distance from our center to our foci, is 5. Now we can use the a squared plus b squared equals c squared in order to solve for b squared. So we have 3 squared is 9 plus b squared is equal to c squared is 25. Subtract our 9, and b squared is equal to 16. So we have a 16 in there. And there's our equation. You don't have to write the equation in standard form. This form is actually preferred because you can tell things from it. You can tell where your center is, you can easily find your vertices, your foci, etc. All right, last example for this one. We have 2 microphones. They're 1 mile apart, and they record an explosion. Microphone A receives the sound 2 seconds before microphone B. Where was the explosion? And we also are going to assume that sound travels at 1,100 feet per second. One other little hint that I'm going to give you here is that your answer is going to be an equation. Because with this information, really, where is this explosion? It can occur anywhere on a branch of the hyperbola. So an extra hint is that the answer should be an equation. And why I like that hint is when we think of where is the explosion, it seems like it should be an exact point, but really with the information that they gave, it can occur obviously in many, many places. So I have my 2 microphones. They're 1 mile apart, but this is, they tell me our sound travels 1,100 feet per second. Therefore, I'm going to write my miles in terms of feet so that I have obviously the same units here. So if we have 1 mile, I know that that's equivalent to 5,280 feet. And with that situation, I'm going to draw a picture. Pictures are worth 1,000 words. Helps out a lot. And I'm going to assume that my center is right at the origin. Because when you make a picture where you have a word problem, oftentimes you want your center to be at the origin, and most of the time it's going to be able to be there. So our microphone A, I'm going to just put that over here. Here's microphone A. And equal distance over here will be microphone B. Well, if these two microphones are 1 mile apart, here's my 1 mile, I better divide that by 2, and that will give me 2,640 feet. And remember, these are your microphones, so your microphones are going to be serving as your foci. And when they hear the explosion, your explosion is going, or the sound that they receive is going to be somewhere on these branches. And I'm just going to put in branches. They don't have to be accurately drawn, but just to get a general idea of what we're dealing with. But one nice thing that we've found already is if I know the distance from my center, because how I've set this up is that my center is at the origin, my microphones are evenly spaced, that tells me that A has to equal 2,000, or I'm sorry, not A. If I'm going from my center to microphone A, which is a foci, that would be C. So C is equal to 2,640 feet. From here, what we have to calculate next, because we want to figure out where this explosion is happening, and the hint is we should write an equation. Assuming that sound travels at 1,100 feet per second. With that information, and sorry, we have another thing in here, is that microphone A receives the sound 2 seconds before B. Well, looking at our graph in a relationship that I didn't state above, that is true for hyperbolas, thinking about the definition, if I take this distance, which I'm going to call distance 1, and then it tells us in the definition that we want the difference. So if I subtract this distance to my other microphone, distance 2. Well, if I have distance 1 and subtract distance 2, so instead of, if I have it and I'm really distance 2, if I subtract it, I don't really want to subtract it from here. So here's distance 1. If I subtract distance 2, this distance is the exact same thing as if I subtract it from there. Because really, like, to subtract it from here doesn't make sense because it really didn't exist there. So distance 1, if I subtract out distance 2, which is the distance from my microphone to my vertex, well, that ends up just giving me this distance here, the red line in between. Well, I know if I go from my center to my vertex, that is always A. So in this situation, this is equal to 2A. Now if we put this into account for what we're dealing with this particular problem, if sound travels at 1,100 feet per second, microphone A receives the sound 2 seconds before B, what we can do is say that if we take that 1,100 feet times our 2 seconds, actually this would be feet per second, so the seconds would end up simplifying out. This is equal to 2,200 feet, which means it's 2,200 feet further from B, meaning microphone B, than from A. Seconds, again, they simplify out. So it's 2,200 feet further from B than from A. So if it's 2,200 feet further from B, what that means is that this distance And remember, it's, sorry, it's the red distance here. I know that I highlighted this part. Because it's that much further from B. So I only want this distance, 2,200 feet further from B. So that distance then from A. Remember, these two distances are equal, so we can't account for them. That tells us that that 2A is equal to 2,200 feet. Well, now I can divide by 2, and A is equal to 1,100 feet. Well, if I know A and I know C is 2,640 feet, I can find B using our Pythagorean theorem, and then I can write the equation. So remember, it's A squared plus B squared equals C squared, so I'm going to take C squared, so 2,640. I'm going to subtract A squared and take the square root, obviously. Gives me a pretty nasty looking number. I'm going to write it as B squared because I want that for my equation anyway. And B squared is 5,759,600. And that I just left it as B squared because the square root of B is not a nice integer. But now I can write my equation. So according to how I set this up, and obviously you could, because it's a word problem, you could set it up differently. But my transverse axis will be it's horizontal, so x will come first. So I have x squared, my center's at the origin, so I don't have to account for any shifting here, minus y squared. I know that has to equal 1. Well, a squared, the distance from my center to my vertex, I plug that in, 1,100 square it. We get 1,210,000 minus our b squared, minus y squared divided by our b squared, which is 5,759,600. Therefore, what that tells us is that to answer the question, here's our equation, and then it would just mean that this occurs somewhere on the right branch of this hyperbola. That really it could occur anywhere because this would be the equation that would set up this particular solution. So, or maybe situation is better. So then just to write in there, the explosion occurred somewhere on the right branch of the hyperbola. I don't know if occurred has one R or two R's. I'm a terrible speller. Just make it sloppy and no one will know. Somewhere on the right branch of the hyperbola. And that's a tough question. Most of them aren't that difficult, but that one is incredibly tough. I thought we should have a tough one in there. Everything can't be too easy. So here's the second part of this assignment then, which maybe you wrote down yesterday anyway. For ellipse and hyperbola, page 704, 33, 35, 41, 43, 49, 53, 57, 65, 96, 98, 101, 103, 107, 113, and 119. And this is everything with the conics, so it's kind of a good thing. It's a crash course of conics, that's for sure. Compared to the first time that you learned conics, and you learned it over many, many days. It's a good crash course for us. Good luck. Peace out.